Okay, perfect. So our focus today is on the 10 transformations of functions. Let's say f of x here is the mother function. Normally, the mother function is a function with the simplest form. For example, quadratic function. We know the standard form of a quadratic function is y equals ax squared plus bx plus c, right? The graph of a quadratic function is a parabola. It's a vertical problem. Either opens upwards or opens downwards, right? The mother function of all the parabolas is y equals x squared. So the simplest quadratic function is this square function. We call the function square function. The machine produces output equal to square of the input. For any given input x, the corresponding output is always equal to square of the input. That's the reason we call the function square function. Again, square function is the simplest parabola. So for quadratic function, we normally see x squared, this function, as the mother function. Similar with other type of function, all right? Similar with other type of function. So f of x here represents the mother function. We want to do something. We want to apply certain treatment, a certain treatment or certain treatments. And those treatments are called transformations. We only learn 10 types of transformations. We want to know for each transformation, how we change the mother function. How do we transform the mother function to the daughter function? And how the graph of the mother function change to the graph of the daughter function. So that's the focus of today. The first transformation is we add a number. We add a number. The number here is a positive number. For convenience, I use a whole number 1. The number could be a decimal or fraction. I use 1 just for convenience because it's a very simple number. So what if we add a 1? The transformation is we add 1 to the function, to the mother function f of x. What do we have? And the change, what's the corresponding change that happens to the graph of the mother function? So we want to use the absolute value function as a demonstration, okay? Let's say the f of x here is absolute value of x. You're going to see this type of function a lot. It has a name. It has a name. This function is called the absolute value function. All right. The absolute value function has a domain all real from negative infinity to positive infinity. The graph of the absolute value function is this graph. I suppose to have an arrowhead here and here to indicate the domain of the absolute value function is all real. The reason I do not have the arrowhead is because I want to be able to move the curve and show you the transformation, show you the change of the curve. But if I move it, I don't have the arrowhead followed. So that's the reason I do not have the arrowhead. Just know it's extending to infinity, okay? Let me erase those. Also, I want to make the graph simpler. So this is the graph of the absolute value function. Domain is all real from negative infinity to positive infinity. Range is all positive, so and 0. So it's from 0 to positive infinity. 0 is in the range because 0, 0, the point here. How do you say this point? You see what I'm talking about, right? The minimum point is at 0, 0. So 0 is in the domain, also in the range. So that's the absolute value function. We see this function as a mother function. Now we are going to talk about the daughter function g of x. What's the daughter function? The other function is g of x equals f of x plus 1. Do you guys remember f of x is just y? So basically our transformation, our treatment here is to add a number 1 to the y value. Let's see what happened, okay? Let's see what happened. I'm gonna make a table here for you. This is x, this is f of x mother function, this is g of x daughter function. So I'm gonna randomly pick some numbers, let's say -2, -1, 0, 1, 2, just for convenience. So when x assume value -2, f of x, the mother function, which is the absolute value function, equals 2, right? Yeah, so knowing f of x is absolute value of x, g of x daughter function is the mother function, just add 1. So when input is -2, output is +2, absolute value of -2 is 2, right? Do you guys so far so good? When x is -1, f of x, the y value is +1, right? When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. So far so good? Guys?
Yeah, I understand.
Okay, perfect. I'm just filling the blanks in the table. Okay, so what about the g of x? When the input, when the x value is -2, g of x is absolute value of x plus 1. So do we have 3 here? Absolute value of -2 is +2. +2 plus 1 is 3, right? And when x equals -1, g of x, the daughter function, is mother function plus 1, which is 2. When x equals 0, daughter function is the mother function value plus 1. So all the corresponding y value of the mother function gonna add up by 1, increase by 1. So 2 here and 3 here. So if we plot those points on the graph, the mother function has 0, 0 here, 1, 1 here, -1, 1, 2, +2, and -2, +2. Those are the 5 points on the mother function, right? And what about the daughter function? X value remain the same, but the y value all increase by 1. So 0, 1, 1, 2, as you can see, 1, 2, right? 0, 1, 2, 3, -1, 2, -2, 3. So this also go up, and -1, 2, -2, 3. So basically, the daughter function, the graph, this is the graph of the daughter function. The daughter function graph is, we can get the graph of the daughter function by move the mother function graph upward 1 unit. So that's what happened when we apply the transformation, add a number to a function. Since the number is added to y, very important, the number is added to y, x value does not change, y values change. How do the y values change? It's very obvious. Y values just add by 1, right? So go up 1 unit. So I want to show you the idea. So this graph is the mother function, absolute value function, right? If we add 1 to the function, to f, to y, we just need to shift the graph upwards 1 unit. Now this graph is the graph of the g of x, the daughter function. So we can summarize, when we add a number here is a positive, by the way. When we add a 1 to the function, when we apply this treatment, the change to the graph of the mother function is the graph shift upwards 1 unit. Do you see it, guys? Is that clear?
Yeah, I get it.
Yeah, this treatment, this transformation is not a challenging one. This is the simple one. Okay, similarly, number 2, What if we subtract 1 from the function? What do you think what would happen to the graph of the mother function?
It'll shift downwards one.
Yeah, shift downwards. Very good. Shift downwards. Let me write it down. Shift downwards 1 unit. Exactly. Very good. Again, the treatment is on y. F of x is y. So all the y value gonna reduce by 1, but x values doesn't change. So that's the reason the transformation is not horizontal. The transformation is vertical. So let me go back. Let's put the graph back to 0, 0. This is the mother function, absolute value function. And if we subtract 1 from the mother function, and we're going to shift the graph downwards 1 unit, right? Yeah, x value doesn't change. All the points on the graph, x value don't change. The corresponding y value reduced by 1, so go down 1 unit. What if we subtract 5 from this function? Then we just need to shift the graph downwards for 5 units, right? All the way to here. You see that? So that's the first 2 transformations. Adding or subtracting a number from the function. When we say the function f of x, that means the y value, dependent variable. Dependent variable. So far so good? Those are the first 2 transformations. You can understand those 2 together as a pair. Next, number 3. Number 3, the transformation, the treatment at number 1 happened to variable x. You see the difference? Do you see the difference between number 1 and number 3? Number 3, in number 1, I added the 1 to y. But in number 3, I added the 1 to x. The input changes, right? The original input is x. Now the input is x plus 1. And what kind of change is going to happen? So we're going to use the same function to demonstrate the changes. In this case, the daughter function is different. This time, number 3, the daughter function is f of x plus 1, right? So our g of x is absolute value x plus 1. This is our daughter function. On the left side here, mother function, absolute value function, absolute value of x. Daughter function, absolute value of x plus 1. This time, the number 1 is added on the input on x, not y, on x. Let's see what happened to those points, right? See what happened to those points. I'm gonna add one more column. Here's x, here's g of x, right? Right. So 2, 1, 0, 1, 2. Again, f of x is absolute value of x. G of x is absolute value of x plus 1. All right. So as you can see, the first two columns give us 5 ordered pairs. Those 5 ordered pairs are the 5 points on the graph. Of course, on the graph, we have infinitely many points, right? I just randomly pick some convenient points here. So we have this point, this point, this point, this point, and this point. Right? So the daughter function right now is absolute value of x plus 1. In order for the daughter function to reach the same output, to reach the same y value, let's see what happened to x. Because this time, the treatment is applied on x. So in order for g of x to produce output 2, what's the value of x? In order for g of x has a y value 2, x has to be what?
1.
Yeah, 1. Actually,
Or -1.
-1 doesn't work. 93 works. We actually means 93. 93, right? In order to reach the same y value, x value, the value of x in a daughter function has to be 1 less than the original x value. Because the input here, in the absolute value, we have x plus 1. So, it means in order to reach the same y value, x do not need to be 92. 93 would be enough, because 93 plus 1 is 92, and the absolute value of 92 is 2. Similarly, in order for g of x to get output 1, the input can be 92, right? Yeah, all the input should be 1 less than original value. This is 91. When you plug in 91 plus 1, 0, absolute value of 0 is 0, right? And in order for, this is because it's symmetric. So we have this one's 0. When x equals 0, we have absolute value of 0 plus 1, which is 1. And here is 1. 1 plus 1 is 2. Absolute value of 2 is 2. So I want you to see this pattern. For the mother function and the daughter function to reach the same y, the x in the daughter function has to be less than 1, has to have the value 1 less than the original x value. So now these two columns, the column 3 and the column 4, give us another 5 points. Let's plot the 5 points. We have 93, 2. We have a -2, 1. We have -1, 0. We have 0, 1. We have 1, 2. Do you see what happened? This is the graph of the daughter function. This is the graph of the function when we add 1 to the x. The graph shifted to the left 1 unit. Do you see it? This part might be the challenge, one of the challenging parts. When we add 1 to x, the graph of the mother function shifts to the left 1 unit. Do you see it? The reason is because the value of x, you add 1 to value of x. So in order to reach the same y, in order to reach the same height, x do not need to, for example, in order to get a 0, in order for the daughter function to get a 0, x doesn't need to be 0, because already you have plus 1 here. So x has to be -1. So 1 less than the original value. So all the x values is smaller, 1 unit smaller. So horizontally, we shift the graph to the left 1 unit. Please let me know, what do you think?
I think I get it.
You get it, perfect. What about other students, please?
I get it.
Okay, cool, very good. Yeah. So the common mistake here is when you add 1 to the function, you go upwards, kind of like very intuitive. When you -1 from the function, you go down 1 unit. However, when you add 1 unit to x inside the parentheses, you shift the graph. Oh, sorry. You shift the graph to the left 1 unit. That seems a little bit anti-intuitive, but that's the correct change to the graph of the mother function. When you add a 1 to x, x has to be smaller in order to, assume so x has to be smaller. We need to know the input is not x anymore, okay? The input is x plus 1. So since your input is x plus 1, the value of x has to be 1 unit smaller in order to produce this, for the function to produce the same y. So all the x values have to be 1 unit smaller. That's how the graph of the function shifted to the left, horizontally to the left 1 unit, because to the left is getting smaller, right? And what do you think of number 4? Transformation number 4. When we minus 1 from x, again, x, this function, x is not input anymore. X minus 1 is the input, right? Since x minus 1 is the input, in order for the function to produce the same y value output, x has to be 1 unit bigger in order to have the same input, right? X value, so x here is not input, x minus 1 is input. So x here has to be 1 unit bigger to kind of like balance the -1 in order for the function to produce the same y. So the y value keep the same, x value has to be 1 unit bigger. The graph, what happened to the graph? Shift to the right 1 unit. Yeah, number 3 and number 4 is the challenging part because it's a little bit anti-intuitive. It's different from 1 and 2. Vertical is very, comfortable, right? How come when you add a 1 to x, you're gonna go left 1 unit, and you minus 1 from x, you go to the right 1 unit? I explained. I don't know if you see it. Let me do one more time. So for number 4, when we minus 1 from x, look at the daughter function. The x is not the input of the daughter function. We are talking about this function. X minus 1 is the input, right? Yeah, x minus 1 is the input. So in order for that input to produce the same output, x has to be 1 unit bigger. The value of x has to be 1 unit bigger in order to have the same input with the mother function, right? All the values of x have to be 1 unit bigger. All the values of x 1 unit bigger. So the graph of the mother function shifted to the right 1 unit. Any questions, guys? You need to make an effort to memorize this part. You probably will not think about what I just explained every single time. So you would need to understand and then memorize. Understand, memorize. So far, so good?
Yep.
Okay, very good. I'll try to hurry up because half an hour we only did 4 of them. Number 5 and number 6. So the transformation or the treatment that happened to number 5, number 6. What happened to my, okay. Number 5, number 6, the treatment happened to y, okay? Again, f of x is y. So here we multiply y value by 2. And here we multiply y value by half. So when we multiply the function, when we multiply the y value, the function by 2, we stretch the function vertically by a factor of 2. Okay, so this should be easy to understand. When you give the input x, the same input, the corresponding output is always doubled. All the y values doubled. So the graph will be stretched vertically by a factor of 2. For the same input, the output always twice of the original, twice of the mother function. Is that understandable, guys? So if you multiply the function, again, function f of x is a y. When you multiply the y by 2, y is vertical, right? Y-axis is the vertical scale. So for the same input, all the output is twice bigger. So the graph will be vertically stretched by factor 2. Similarly, if you multiply the function f of x, y value, again, f of x is y, by 1/2, a number less than 1, that means the y value is smaller than the original y value, right? So for the same input, all the outputs become half size of the original y value. So in this case, we vertically compress the graph by a factor of 1/2. Okay, like all the y value become half size of the original. Let's see if I can explain that. So let's try this graph. This is the simplest quadratic function. Let's see, f of x is x squared. The domain of the function is all real. Yeah, we should have an arrowhead here. The reason I do not have it, same with earlier, because I want to be able to, when I move the graph, I can just move one piece, right? I tried earlier to just draw the whole thing with the arrowhead one time, but it didn't happen. Pretty challenging. So this is the problem. Domain is all real, range 0 to positive infinity. Okay, so this is the mother function. So we want to talk about the daughter function. G of x equals 1/2 x squared. So the daughter function, we got the daughter function by multiplying the mother function by half. All the y value will become half size of the original y value. So let's see what happened here. Let me make a table here. This is x, this is f of x. F of x is x squared. This is g of x. G of x is 1/2 x squared. Let's try -2, -1. Why do I choose those numbers? Just because they are convenient. 0, 1, 2. When I'm going to quickly plugging in the input to have the corresponding output for function f, okay? When x is 92, 4, 91, 1, 0, 1, 4, all right? And let's see if we plugging in x, the input for x, the value for the input, what's the corresponding output for the daughter function, okay? See, the daughter function is just 1/2 of x squared, 1/2 of the y value. So all the y value is going to become its original, half of the original. So half of 4, 2, half of 1/2, half of 0, 0, half of 1/2, half of 4, 2. Okay, so now let's see the graph, the 5 points on the daughter function. We have -2. So how do we see that? This is a pair, okay? That's a pair for the daughter function. Another pair, another pair. So we have 5 pairs. We have 5 points. They are -2, 2. -2, 2. We have -1, half. -1, half. It's right here. 0, 0. Still here. 1, 1/2. See here. And 2, 2. Hold on. 2, 2. Yeah, 2, 2. Right here. All right. Yeah, my graph is not very accurate. So as you can see, this is the daughter function graph. The red one is the mother function. So as you can see, if we multiply the mother function, the y value by half, the graph of the mother function is stretched horizontally. Okay, how about this? Vertically. Let's do that. Vertically, like you have a hand. This is your hand. You just push it down. Push down the graph. Vertically shrunk or compress. All the y value become half of the size, right? Half of the value. So it's like when you push something down, would that make the thing become fatter? That's what happened to the graph. All right, I hope this is understandable. On the mother function, this is 92,4. So the same point, just the y value shrunk to the original half of the original size. So that's why it go down. It went down. When you vertically compress, you would have a fatter graph than the original. Please let me know if that understandable. Number 5 and number 6. When we multiply the function by a number, positive number bigger than 1, we would have a vertically stretched graph. When we multiply the function by a positive number less than 1, then we would have a graph vertically compressed. So far, so good?
Yep, I understand it.
Okay, perfect. Number 7, number 8. The treatment for number 7 and number 8 happen to x. All right, like this one, f of 2x, the daughter function. So the 2 here is not multiplied with the y value. Instead, the 2 here is multiplied with the x value. So that would happen. Actually, this one is also a little bit anti-intuitive. When you multiply 2 to x, we multiply x by 2. The whole graph would be horizontally compressed. Okay, horizontally compressed. So in order to demonstrate that, I'm gonna use this function. And we know the name of the function, right? This is the absolute value function. This is the famous square function. And this is the square root function. Okay, we're gonna learn a new function, square root function. F of x equals square root of x. I think I talked about the radical a little bit in previous section. A radical has 3 parts, right? Root number, radical symbol, and radicand. And you should remember this name. So when you do not see the root number show up like this function, that means it's defaulted as 2. That's why this is a square root function. All right, this is the simplest square root function. F of x equals the square root of x. The domain of the function. Remember, when the root number is even, the radicand cannot be negative. So the domain of this square root function is all positive and 0. So bigger than or equal to 0. X cannot be negative. And the range of the function is also 0 to positive infinity. And the graph of the square root function is this. Okay, again, it's supposed to have a arrowhead here. There's a solid dot here, there's an arrowhead here. You know, the graph only appears in quadrant 1 because the domain and the range both are from 0 to positive infinity. So the graph of the square root function only appears in quadrant 1, and the continue goes up but concave down. Yeah. Again, the reason I do not have the arrowhead is because it's for convenience, all right? And you know it's continue. So our daughter function here, g of x is f of 2x. We multiply the x by 2. And so we have a square of 2x, right? Let's see what happened to the daughter function. Let's see what happened to the daughter function. Since the treatment happened to x, we're going to do 4 columns. This is f x, this is f of x, this is x, this is g of x. F of x is root x, g of x is root 2x. All right, we found some convenient number to see the pattern. We're going to do 0, 1, 4, see 9, no. How about just those 3 points? Just those 3 points. Let's see what happened. So when x is 0, root x is 0. When x is 0, when x is 1, root x is 1. When x is 4, root x is 2, right? Okay, now we want g of x achieve the same value, the same output. We want the daughter function produce the same output, 0, 1, 2. And let's see what x assume. In order for root 2x to be 0, x has to be 0, right? And that one is just a special. But in order for root 2x to be 1, x has to be what? Do x have to be half in order for that to happen? Right? In order to have the same input, again, the input is not x anymore. The input is 2x. In order for the input to be 1, the same input, the x value has to be half because it's 2x, right? Then in order for root 2x to be 2, x has to be 2. So in order for the input, which is 2x, assume the same value with the mother function, x has to be half smaller, right? Half of 0 is still 0, half of 1 is half of 4 is 2. So let's plot the 3 pairs for the daughter function. Let's see what happened to the graph. The original 3 points are 0, 0, 1, 1, 4, 2, right? And let's see what happened to the daughter function's graph. We have 0, 0, that's still here, and a half, 1, and 2, 2, 2, 2, 2, 2, 2. Hold on. Half, oh, sorry. Half, 1 is not there. Half is here. Half, 1 is here, right? Half, 1 is here. And 2, 2 is here. So we connect those. Of course, more point is better, but it's also time consuming. So this is the daughter function, root 2x. The red one is the mother function. The black one is the daughter function. So when we multiply the x by 2, since in order to reach the same output, value x have to be half smaller, you actually horizontally compressed. This is your hand. You horizontally compress the curve, horizontally compressed by a factor 2. So all the x values become half of the value. So that's why the graph looks like a taller, because you compress horizontally. I tried my best. I don't know if that really helps you. You do need to understand why. Otherwise, it just loses the meaning. Again, the function, the input of the function, let's go back to number 7. The input of the function is in the parentheses. The input right now is 2x. X is not input anymore. So in order for the function to have the same input and also have the same output, the x value has to be half smaller. Imagine all the x value become half smaller. So that change happened horizontally. So that means horizontally the graph is compressed to the half size of the original, right? Some response, please.
Yeah, I'm just, do we have to, so we should just memorize kind of how they.
You're supposed to understand, what I just taught.
It's a
little tough, right? So do you understand that this, the blue, remember, whatever inside the parentheses, that's the input. So the blue 2x is the input.
Yes.
So for that function to assume the same input, have the same input, x has to be half smaller. The value of x has to be half smaller, right? Because the input right now is 2x. In order to have the same input, x have to be half smaller. Imagine all the x values is half size. Then that make the graph horizontally shrunk or compressed. It's just that if this input assume 1, if you want the input to be 1, for the mother function x is equal to 1, no problem. Here, I thought about, do I need to spend time to talk about this so much? I think yes, we need to understand. We need to understand it. But for the same function, if you want this input to be 1, x cannot be 1, right? If x equals 1, the input is 2. So in order for the input to be 1, x has to be half. You see what happened? So to guarantee the same output, to make sure the vertically doesn't change those values, and the x values have to be half the size of the original. So that's why horizontally shrunk. Oh, I tried. You can rewatch this part and, maybe digest it later. I know this part is challenging. It's okay if the first time it doesn't really click. And similarly, but if you multiply x by a number, positive number less than 1, you know what happened to the graph? Horizontally stretched by a factor of 2. Same idea. Again, in this case, the input, this is the machine, right? Machine F. You want to have the same output. But in this case, the input is half x. In order for the input to produce the same output, you want to keep the same input, right? The same function, you want to have the same output, you need to give the correct input. But in order to give the correct input, for example, 1, you want the input equals 1, right? X cannot be 1, x has to be 2. The mother function, the input is 1, but the daughter function, when the mother function, when x is 1, the input is 1. But the daughter function, when x equals 2, the input is 1. So all the x values have to be twice big in order to have the same input and then go through the machine to have the same output. So all the x values doubled. So horizontally, the graph is stretched by a factor of 2. Okay, try to digest, all right? If not, then I don't know. I think all it matters is you know how to do the problems, right? Yeah, just bear with me. I do need to, if I don't do this, I don't feel comfortable. I have to explain why. Last 2 is easier. Yeah, I know this is challenging. This 3 and 4 is challenging, and 7 and 8 probably more challenging than that. The last 1 pair is easier. If we multiply the function by -1, the graph of the mother function will be reflected or flip. I'm gonna type flip You can say reflect with respect to or flip. You can find the correct English. Flipped with respect to or over y-axis. If you multiply x by negative, then you flip the function over the x-axis. Oh, my bad. This is x-axis. And this is the y-axis over the x-axis. So this is over y-axis. Y-axis. Okay, let's take this graph as example, right? The square function. The 5 points, 2, 3, 4, negative comma 4, actually, it's right here. So the Mother function right now, this Mother function is square function f of x equals x squared. The daughter function is negative x squared. So the whole function is multiplied by -1. You are taking the opposite of y, not x, okay? You're multiplying the function by -1. So daughter function is negative x squared. So when x is a -2, y is gonna be -4. When x is -1, y is going to be -1. When x is 0, is 0. When x is 1, is -1 here, and this is -4. So for the same input, just think about, for the same input, the mother function produces a positive output, right? For the daughter function, with the same input, the machine of the daughter function produces the opposite of the output of the mother function. All the output, all the y value become the opposite. So we have -4, -2 comma -4. We have -1 comma -1. We have 0 comma 0. We have 1 comma -1. We have 2 comma -4. So this is the graph of the daughter function. When you multiply the whole function by -1, you mirror the graph over x-axis. You can see the x-axis as a lake, the surface of the lake, right? So the daughter function is just the shadow, or the reflection of the mother function. So you need to understand this in order not to memorize a lot of things. So I am a person do not like to memorize a lot of things, so I understand. Worst case, I just derive, right? I remember as little as possible. I only remember the most, important and very necessary. And other things I just derive. If I understand, I can just get it out, figure it out. All right, here, if we multiply the whole function, multiply the y value by -1, the graph will flip over x-axis, like what I just showed you. And what if the negative sign is applied to x, the input? Then the graph would be flipped over the y-axis. We're gonna take this square root function as an example, all right? Square root function. Oh, so I'll just redo it. So square root function has domain range from 0 to infinity, okay? And the daughter function this time is root negative x, right? And just the thing about what's the domain of the daughter function, guys? This is from previous section. The daughter function is the square root of negative x. Anybody can help me to figure out the domain. The root
Negative.
number is 2. Negative infinity to 0, right? Exactly. X here cannot be positive because if x is a positive, negative x is negative. So the radicand become negative, then the square root function is not meaningful, is meaningless, is not defined. Remember, the radicand has to be positive. Whatever under the square root has to be non-negative, right? Bigger than or equal to 0. So the radicand here is negative x. The radicand has to be bigger than or equal to 0. From foundation 2, you know, if we divide or multiply each side of an inequality by a negative number, you have to flip the direction of the inequality symbol, right? So divide by -1, divide by -1, we're going to flip the symbol. We have x is less than or equal to 0. So the domain of the daughter function is all negative, including 0, okay? All negative. So the graph is like this. Is flipped respect to y-axis. Y value, in order to have the same y value, x has to be the opposite of the original value, right? So x cannot be positive anymore, it has to be negative. That's why you flip over y-axis. And so I would recommend that you remember the square root function. When you multiply x by -1, what happened to the function of the graph of the function? The graph will flip with respect to y-axis. It will not be flipped, reflected with respect to the y-axis, okay? Because if you do that, this function still has domain positive, and that is incorrect. Because the radicand has to be non-negative, so x has to be negative or 0. So it has to be on the other side. Okay. Yeah, finally, yeah, one hour to explain the 10 transformations, I think is necessary. Otherwise, if you don't understand a thing and you just memorize for the purpose of the test or assignment, it doesn't stay with you. When you go to calculus, you're gonna need those again. So focus on understanding, all right? I'm recording the class. Just double check I'm recording it. Someone leave me a message.
It said
Okay.
it was recording when I got on.
Yeah, it's recording. So how do we know that? It's right here on the top right. I saw it. All right, finally, we can do some problem, right? Yeah, we have more here. Number 11. So what do you think? The mother function is the square root function. The daughter function is square root of x plus 5. So the treatment or transformation is we add number 5. We add 5 to x. You must be very clear what's the treatment. The treatment is applied on the x or applied on the y. It makes a huge difference. So this time the x is applied on x at 5. So how the graph change? How will the graph of the mother function change to get the daughter function graph?
Is it gonna move to the left by 5?
Perfect. Let's shift to the left. 5 units. Very good. Because the treatment is on x. So for us to have the same input, x need to be 5 units smaller. All the x become 5 units smaller, so the graph shift to the left 5 units. What about number 12? This is the famous absolute value function. You need to know the graph of the absolute value function. And the daughter function is subtracted 2 from x. Okay, the treatment is on x. Vertical or horizontal?
Vertical.
X minus 2. The treatment is on X, so it should be horizontal. Right? Horizontal, shift to the left or right. Okay, guys. If the treatment is on X, it's gonna be horizontal transformation. If the treatment is on Y, that is the vertical transformation.
Yes, sorry. I mixed that up.
Yeah. So you minus 2 from X, you minus 2 from X. So the horizontal treatment, the horizontal transformation. How it change horizontally? The whole graph is gonna shift to the right 2 units, right? Because X has to be 2 units bigger in order for the function to have the same input and the corresponding output. Number 13, the mother function is the famous square function, and the daughter function is multiply the whole function by -1. So here we multiply y by -1. So how the graph change? Multiply y by -1. So it's also a vertical change, right? You just flip the graph over x-axis, right? Flip the graph, flip or reflection over x-axis. We actually have this right here, right? If you multiply y, the whole function by -1, the whole graph gonna mirror to the below the x-axis. Flip over x-axis. Flip over x-axis. What about number 14? We saw this already, right? This time, number 14, the treatment happens to x. So the -1 is multiplied with the x. So the graph is going to be reflected over y-axis. We have the same problem earlier. It's a good function to explain this transformation. Mother function f of x is root x. The daughter function is square root -x plus 1 minus a, which actually is negative x minus 1 minus a, right? So 3 steps. Let me draw the mother function graph first. This time, let me try if I can get an arrowhead. See if it stays. Okay, it does. Okay, perfect. So what happened is we firstly shift to the left 1 unit. And then flipped over. Does that let me to flip over? Oh no, hold on. I probably have to draw it again. So flip over y-axis. Use a different color. This color. It's gonna be like that. All right, now it's supposed to be symmetric. Flip over. And then go down 8 units. This is the graph. You see that? Shift to the left. What? Hold on. My bad. Shift to the right. I made a mistake. I apologize. Shift to the right. Shift to the right 1 unit. Okay. Shift to the right 1 unit. Shift to the right 1 unit. And then flip with respect to y-axis. And then shift down 8 units. So this is the mother function. I apologize. This is mother function. The reason we shifted to the right because the subtract 1 from 1. So shift to the right 1 unit is right here, right? And then flip over y-axis. We should have this piece like that. And then go down A units, right here. And that's the dollar function. Any questions, guys? Yeah, it is easy to mess up this part. -1 from x is not shifted to the left, it's shifted to the right. Because all the x has to be 1 unit bigger in order to have the same input and the corresponding output. Some response?
I understand it. You explained it really well.
Thank you for the positive feedback. I'm trying. I hope you don't see this as wasting time. We do need to understand it for your future. Because pre-cal, I understand, my understanding is if you take a pre-cal, you are actually going to take a calculus, right? Pre-cal, you are preparing for that. So you do need to understand the behavior of those functions when we apply certain treatment. We have 5 more minutes. We have more functions here, more transformation here. Let's finish this. Number 16 is the absolute value function. 3 here is multiplied with the whole function. So we tripled y value. Since we tripled the y value, the change is vertical. All the y value gonna become 3 times bigger. So this is vertically stretched 3 times, or by the factor of 3. And number 17, yeah, number 17 is a good one. I'm gonna start a new page and I can do this here probably. Okay, here. The mother function is cubing function, okay? F of x equals x cubed, which is y equals x cubed. The machine produce output. The output is always equal to cube of the input. So that's why we call this function cube function. Some people say the cubing function, sometimes say cubic function. The same thing. This is the cube function. And what does the cube function look like? This is the cube function, all right? The important point, 0, 0, 1, 1, -1, -1. And the arrowhead means infinity. So this is the cubing function. Our transformation, the dollar function is -x plus 3 to the power of 3 minus 2. So the transformation is more than 1. Let's do it by steps, okay? Let's do it by steps. We start from the mother function f of x equals x cubed. First step, we look at the adding 3, right? Yeah, first step is adding 3. The 3 is added to input. 3 is added to the input. So the horizontal change is a horizontal shift. Shift left or right, guys? Add a 3 to the input.
It'll shift left.
Perfect. Shift it to the left 3 units. All right? Okay, so now we have, yeah, that's the mother function. We have, now the function is x plus 3 to the power of 3, right? And next step, we multiply 1. So this is the treatment. Multiply -1. Multiply what by -1? Multiply the whole thing. Multiply this whole thing by -1. So the treatment is on y. we multiply the whole function, this whole function by -1. Okay, next step, we multiply the whole function by -1. So the treatment happened to y value. So it's a vertical change. So it's a flip or reflect over x-axis or y-axis. It is the x-axis because the vertical change means a flip from top, like a, I don't know how to put it in the right English, like a flip from top to the bottom or from bottom to the top, right? It's not from right to the left or left to the right. So it's a vertical change. You flip over x-axis. And now you have this function, right? We are making progress. And last step. So now we have this function. The last step gives us the dollar function is subtract 2. We subtract 2 from the whole function. So the change happened to y. The change happened to the output. So that is vertical change, vertical shift downwards 2 units. All right, shift downwards 2 units. Let me see if I can do this. Oh, yeah, actually I could. But the coordinates gonna change, okay? The coordinates gonna be different. So basically, we should have, let me erase those points. The coordinates, I mean. Okay. So firstly, shift to the left 3 units. Huh? It doesn't really let me do it. Oh, yeah, it does. So 3 units, 1, okay. I first have to give the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So we shift to the left 3 units and flip over x-axis. So how do you flip over x-axis? Flip over x-axis is gonna be like this, guys. And then shift downwards 2 units. This piece go downward 2 units. And like that. All right, sorry that we don't have a chance to look at the problem on Lumen. But I think it's necessary. What happened to this chapter is last section is about circle. I do not plan to spend too much time on that section. So we would have some time talk about the more important sections. In the exam 1 about circles, you only have 1 question about circles. You just need to know the formula. That's it. So we are not going to spend like 80 minutes on that. So we're gonna stop here. And next time on Tuesday, we are going to spend some time to reinforce what we learned today about the transformation. And we're gonna work on some problems together in Lumen. Okay. Today we don't have the time for that. Thank you so much for coming. I'll see you guys on Tuesday. You guys have a good weekend. Bye-bye.
Have a good weekend. See you
Bye.
Tuesday.
Thank you, you too.
Thank you. Goodbye.
Thank you. Bye-bye.